Okay, so we're going to be looking at the binomial distribution. So binomials are just expressions with two terms in them. So as we can see here in this first expansion here, we have a plus b. So a is one term, b is another term. And we're going to just use a and b to start, and we'll introduce some more things into it a little bit later. So the binomial theorem is all about expanding these. So putting the sum of two terms to some exponent and then seeing what we get. So if we put anything to the power of 0, we get 1. So that's our most basic expansion. We did a plus b to the power of 1. Well, that doesn't really do anything, right? You just get a plus b. But it starts to get interesting when we do a plus b squared. So if we had this would be equivalent to, say, something like a plus b times itself, a plus b. And we know how to expand something like that. We can FOIL, right? So we'll speed through that a little bit because we've FOILed before. So we do first a times a squared, outer, a times b, so plus ab, inner, b times a. Instead of writing ba, we'll write ab again. The order we write the terms in doesn't matter if they're multiplying, because the order of multiplication doesn't matter. And last would be b times b, which would be plus b squared. And we have some like terms we can collect, and we get a squared plus 2ab plus b squared. So we've seen stuff like this with quadratics, because this is a squared before. Okay, now it gets a bit more complicated as we start increasing the exponents. And that's where eventually our binomial theorem will come in, and we'll come up with a strategy and a technique for expanding these without having to do a lot of work. But we'll do a few with the work to see that it's working. So let's do a plus b to the power of 3. So if we wanted to do this, that would just be a plus b times a plus b times a plus b. Another way we could think of it, though, we can kind of take a shortcut and go a plus b squared times a plus b. Because we already know what this looks like when it's expanded. It looks like this. We can rewrite that as the whole first bracket is a squared plus 2ab plus b squared. And then multiply that times a plus b. Now here we want to expand, but FOIL is only when we have like two terms, like two binomials multiplying each other. So brackets with two terms each. This one has three terms on it. It's got a squared, it's got 2ab, and it's got a b squared in it. But the idea with FOILing is that we're just multiplying everything in one bracket by everything in the other. So we can do that. So everything, we'll start with a squared. So a squared times a cubed, and then we'll do a squared times b, a squared b. Okay, now we got the 2ab next, so 2ab times a. All those a's can square up. 2a squared b, and then 2ab times b. So we have 2ab squared. So the b's can square. Then we do the b squared, and we get plus, and I'll always write the a terms first, just in each term. That way it's a little more organized. So b squared times a is ab squared, and then b squared times b is b cubed. All right, now let's see if we can simplify this, collect some like terms. So there's only one a cubed, and then a squared plus 2a squared is plus 3a squared b. And there's 2ab here and an ab there, so that's 3ab squared. And then there's a b cubed left. Okay, and as you can see, this is becoming a lot of work. It's a lot of algebra, a lot of expanding. If we do the fourth one, I'll write out the first step, and then I'll just show you what the answer is so we don't take so long going through the entire algebraic process. But we could do it like a squared plus 2ab plus b squared times a squared plus 2ab plus b squared. So that'd be This is a plus b squared times a plus b squared. And then we'd expand everything, and we'd end up with like 9 terms. And then we'd have to collect like terms and bring it all together. And it's a bunch of algebra. So this is a possible way to do these expansions, but it's not a very good strategy. So there has to be a better way. And there is a better way. So I'm going to write out the expansion for this, and then we'll talk about it. So what happens if you expand this and you get collect like terms and everything is you get this. A to the power of 4 plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b cubed. Sorry, not cubed, to the power of 4. B to the power of 4 for the last term. Okay. So this is the point in the lesson where if we're all in class together, I would ask you, do you notice any patterns? And you can pause the video for a minute and think about if you can see any patterns. Look through the multiple terms and the multiple ways it worked out and see if there's anything you notice, anything connecting this to the final answer. Okay, and you might be able to read some of these sentences below to get some hints. But one of the things students often notice is that the exponent carries over, right? So this has a plus b to the power of 4. It's the power of 4 is the highest a, right? A to the power of 4 is there, and we have a b to the power of 4. And the sum of all the other exponents on each term is also 4, right? So a cubed, this b to the power of 1, that's 4. A squared, b squared, 2 and 2 is 4. 1 and 3 is 4. 4 and 0 is 4, and 4 and 0 is 4. So there's a b to the power of 0, you could imagine. Okay, so that kind of, a starts at 4 and goes down each term. So it's a to the power of 4, a to the power of 3, a to the power of 2, a to the power of 1, a to the power of 0. B is going up. It's kind of b to the 0, b to the power of 1, b to the power of 2, b to the power of 3, b to the power of 4. And of course, like we could rearrange the order of these, but that's a nice order to have. And generally in math, we try to have descending powers in our term order, descending powers of the first alphabetical variable. So a is the first alphabetical variable in this case. Okay, so that tells us a lot about the exponents, but what about these numbers in front, the coefficients? So let's think back. So here, these first terms always have 1s in front. So 1, 2, 1. Okay. This one goes 1, 3, 3, 1. This one goes 1, 4, 6, 4, 1. Now, does that sound familiar? Those number patterns, symmetrical. It's almost like something we did earlier today. And these coefficients are, in fact, Pascal's triangle rows. So, in general, if we have a plus b to some power n, whatever n is, so it could be like 10. Because you can imagine, like we did even a plus b to the power of 4, we could do that. And we could probably do 5, we could probably do 6, we could probably keep going and going and going, and it'd just be more and more algebra. It gets bigger and bigger and harder, more work. But if we wanted to do like to the power of 11, and 11 is not even a big number, we wanted to do the power of 100, that would be insane, right? By hand, that would take forever. So we don't want to do that. So in general, for a plus b to the power of n, the coefficients, I don't know if I gave myself enough space to write that word in. I'll write it up above a bit. Coefficients are the numbers of row n. And remember, when we talked about Pascal's triangle earlier, we said the top row, that's just 1, is row 0. Okay, so if we think about that, row 0, 1. Row 1 is 1, 1, 1, 1. Row 2 is 1, 2, 1, 1, 2, 1. Okay, so we can see those coefficients happening. So the coefficients are the numbers of row n of Pascal's triangle. Okay. The first term starts with a to the power of n and descends or decreases each term to a to the power of 0 for the last term. And usually we don't write the a to the power of 0 part. We just leave it blank. We could write it in every time. But remember, anything to the power of 0 is just 1. So multiply by 1, doesn't really make a difference. The first term starts with b to the power of 0 and increases each term to b to the power of n for the last term. So here we had n as 4, and we can see fourth row of Pascal's triangle is 1, 4, 6, 4, 1. A starts at 4, goes down each time. And B starts at 0 and goes up by 1 each time until it reaches n of 4. Okay, so that allows us to kind of jump ahead to the expansions. So let's try that for a plus b to the power of 5. So we aren't going to write out the whole thing. The whole process of expanding, we're just going to use binomial theorem. Okay, so first we have to look up Pascal's triangle in the 5th row, and I actually have that. Here we go. So row 5 is 1, 5, 10, 10, 5, 1. So what we'll do is we will start by writing out those numbers. Now I'm going to spread them out pretty good. So 1, positive 5, plus 10, plus 10, plus 5, plus 1. Because I want to be able to fill in some more stuff in here. So, all right. And then a starts at n. So a is going to start at 5. So a to the power of 5. And it decreases each time. A to the power of 4. A cubed. A squared. A to the power of 1. A to the power of 0. Okay. So we know we wrote enough terms because a went to the power of 0 by the end. Looks good. And b starts at to the power of 0 and goes up by 1. So b to the power of 1, b to the power of 2, b to the power of 3, power of 4, b to the power of 5. All right. So that's how we can use binomial theorem to expand these binomials. Now, we don't always just have a's and b's. Sometimes we have other things we want to expand. Any binomial we can use binomial theorem with. So let's look at some examples and maybe a strategy for expanding those. So here we have x plus 2 to the power of 4. So we're going to start by just saying let a be the first term, x, and b equal 2. So this is a thing we do in mathematics just as a kind of temporary substitution. And this one's not too complex. We'll do some more complex ones a bit later. But it allows us to kind of rewrite this in new terms. So now we can write out a plus b to the power of 4. Okay, so let's use our Pascal's triangle to do that. All right, so that's going to be 1 plus 4 plus 6 plus 4 plus 1, a to the power of 4, a to the power of 3, a to the power of 2, a to the power of 1, b to the 0, b to the 1, b to the power of 2, b to the power of 3, b to the power of 4. A good test as well, once again, is to remember that the sum of the exponents should always be n, right? So 4, 3 plus 1 is 4, 2 plus 2 is 4, 1 plus 3 is 4, and 4. Okay, so now we'll substitute these values back in. Okay, so if we want x plus 2 to the power of 4, then we'll substitute them back in. So we don't really need to write the multiply by 1 here. It's nice. I like to write it when I do this first line just because it's denoting the place where I'm going to put in an exponent. Okay, so for replace the a's with x's, so x to the power of 4 plus 4 x to the power of 3, and b will replace with 2 times 2 plus 6 x squared. B gets replaced with a 2 squared. Okay, you'll note I'm very intentionally putting all of these in brackets. That will become very important later. You can put the x's in brackets as well if you would like. Plus 2 power of 4. Okay, so Now we can expand and simplify each of these terms. So x to the power of 4, that doesn't really simplify. Here we have x, or 4x cubed times 2. Now, within a term, the order of these multiplications doesn't matter, right? So we can multiply the 2 and the 4 together. So 2 times 4 is 8. So that'd be 8x cubed. For this term, we have 2 squared. So we have to do BEDMAS within the term still. So that's 2 squared is 4 times 6 is 24 x squared. Here we have 2 to the power of 3 first. 2 to the power of 3 is 8 times 4 is 32x. And lastly, we have 2 to the power of 4. 2 to the power of 4 is 16. All right, and there is the binomial expansion of x plus 2 to the power of 4. Okay, so this is some ways a lot more practical than just a's and b's, right? So the step of transferring between a general expansion and a practical application of that expansion is a useful skill for mathematics. So let's try some more examples. Okay, so a few things different in this one. One, we have two things in our term. We have 2x, but that's fine. Still say let a equal 2x then. And here we have a minus instead of a plus. That's fine, because minus y is the same as saying plus negative y. So we're just going to let b be negative y. And that's where both of these, because there's two values in this term, or two things in this term, and there's a negative in this term, that's one of the reasons it's going to be really important for us to put brackets in. But once again, we'll just start with a plus b. A plus b to the power of 5. Use Pascal's triangle. 1, 5, 10, 10, 5, 1, a to the 5, a to the power of 4, a to the power of 3, a to the power of 2, a to the power of 1, a to the power of 0, b to the 0, b to the power of 1, b to the power of 2, b to the power of 3, b to the power of 4, and b to the power of 5. All right, so now we can substitute them back in and get our 2x minus y to the power of 5. And in this particular case, I'm going to color code a little bit just to make it a little easier to read. I'll put the coefficients in first. So 5, 10, 10, 5. And the 1, I'm not going to write in the end. I'll write a plus for it, and plus is in. We're going to have to change some of these, as you'll see in a minute. Okay, so let's start substituting in. I'll do all the a's first. So when I substitute them in, I'm going to put them in brackets. So we'll get 2x to the power of 5. So when we go to expand and simplify this, we're going to have to do 2 to the power of 5, x to the power of 5. For this one, we get 2x to the power of 4, 2x to the power of 3, 2x squared, 2x, and then we don't get anything there. And I'll do in red for our b values. So b is negative y. So we'll plug in negative y in for each. So negative y squared, negative y cubed. Should have given myself more space here. Negative y to the power of 4, and negative y to the power of 5. Okay, so let's start expanding these. So when we have two terms or two things in our exponent, they both are going to get the exponent applied to them. So 2 to the power of 5, x to the power of 5. So 2 to the power of 5 is 32. Double check my notes. Yep. 32 and x to the power of 5. Okay. Plus 5 times, 2 to the power of 4. That's 16. So 16 x to the power of 4. And then negative y to the power of 1. So what's going to happen here is, well, that's just y to the power of 1. But what about the negative? Well, the negative doesn't get canceled anywhere, so it's going to change the sign of the term. So we're going to replace this with a negative. So this term is going to be a subtraction. Let's go to the next one. Plus 10 times 2 to the power of 3 is 8. X to the power of 3 is just x to the power of 3. Negative y squared, so when we square the negative y, the negative is going to cancel. So this term will remain positive. We'll get a y squared plus 10. 2 squared is 4. X squared is x squared. Negative y cubed. So when we cube a negative, so every odd power, the negative remains. So when we do cubed, it will stay negative. So we'll change the sign in front to a negative. And we're going to run out of space. Okay. This one, I think we can just kind of expand out. So 5 times 2, there's no exponent on our 2x here. So that's just 10x. Negative y to the power of 4, the negative is going to cancel out. We just get y to the power of 4. And lastly, we get negative y to the power of 5. The negative will remain, negative y to the power of 5. Okay, so we're almost done. One last thing, we just have to do these multiplications and we'll be done. So we'll get 32 x to the power of 5. So negative 5 times 16, that's negative 80 x to the power of 4y plus 80 x cubed y squared minus 40 x squared y cubed plus 10x y to the power of 4 minus y to the power of 5. Okay. That one's a lot more work. So once we start getting some more complex terms inside our binomial, then it can be a bit more work still. But if you think about having to write this out and foiling it over and over and over again just to get to the power of 5, that would be way more work. And it's way easier to make a little mistake along the way. Okay. So let's try one more. This one's a cubed, so that's going to be a little bit easier, but it does have some interesting stuff in it, like an x squared. So that's fine. Let a equals x squared. B equals 3y. So let's start by writing a plus b cubed out. So when you kind of have done a few of these, you don't necessarily need to write 1, 3, 3, 1 out. Sometimes it's easier to just kind of go along and write out the entire term each time. So this is going to be 1a cubed plus 3a squared b plus 3ab squared plus b cubed. So while I was going along there, I was thinking, okay, every time I have to write a coefficient, what's the next number in Pascal's triangle? So 1, 3, 3, 1. And then every time I had to write a, I was going down by a power. Every time I had to write b, I was going up by a power. It's a bit more to keep track of at a time. It does let you write it a little neater. You can do it either way. When you get really comfortable with these, lots of people just write it all out at once. Okay, so now let's substitute back in. So we have x squared plus 3y cubed. What would that look like? So let's start swapping them in. So we'll put them in brackets. So x squared cubed. We're going to have to do some exponent rules stuff there, I think. Plus 3x squared squared times 3y plus 3x squared to the power of 1 times 3y squared, our b value, plus 3y cubed. It's really important to be writing, especially these two-term pieces, in brackets. If I just wrote plus 3y cubed without the brackets, almost every student would just end up being like, oh, that's already expanded. And they would forget about doing 3 to the power of 3. So it's really important to be consistent with that. Okay, so our exponent rules for this. When we have an exponent to another exponent, we learned about this earlier this year, we multiply those exponents. This is going to be x to the power of 6 plus, so here we have, we'll have to expand that, and we have a 3 times a 3, so that's going to be 9 x squared squared. It's going to be x to the power of 4 times y. Just the one y, it doesn't have an exponent on it. Plus, okay, so the 3 is going to multiply by this 3, but this 3 is being squared first, so we have to maintain bedmass. So 3 squared is 9, times 3 is 27, x squared, and then y squared. If you want to write these out off to the side to expand them out, or do it in more lines, that's probably a good idea as well. Here we got 3 cubed. 3 cubed is 27. Y cubed. And there's our expansion. So you'll notice with this one, though, our exponents do not add up to 3. This one's 6. This one adds up to 5. This one adds up to 4. This one's 3. Right? The reason that is because one of our terms inside of our binomial had an exponent as well. On our a plus b, then all our exponents added, right? So sometimes that rule of thumb doesn't 100% hold at the end after we've done that substitution back in. All right, that is it for binomial theorem.